In this lecture, we're going to talk about another type of sequential model where the state space is now going to be continuous. So before we discuss this, let's go back and review the previous two sequential models we discussed. The first was a Markov model where we had a sequence S1 through S4 or S1 through ST. And this sequence was observed, and we modeled it as having a Markov property, meaning that for all values t, the distribution on the sequence at time t, given all the previous time points, is only conditionally dependent on the previous time point. So we can throw away all the information in the previous points of the sequence except for the last point. In this case, we assumed that the number of states were finite and discrete, meaning that we could index them with a number from 1 to s. This allowed us to then represent the transition probabilities in a matrix. So we could say that the probability that the state at time t is equal to j, given the state at time t minus 1 is equal to I, is just the ijth value in a matrix, an S by S matrix. We then broaden this definition to define a hidden Markov model. And this was a model where the state sequence still followed a Markov process, but the sequence itself was latent. And what we observed were state-dependent observations from a state-dependent distribution. So in this case, again, the state sequence S1 through Sn followed a hidden Markov chain, but we didn't get to observe it. And then at any given particular time point, say the time point Sn, we observed a corresponding value xn, which was from a probability distribution where the parameter used was dependent on the state. So for example, at time t, the distribution on the observed sequence at time t xt, given the state at time t st, is generated from some probability distribution with parameter selected by the state st. So these distributions were always the same family, but the parameter itself was state dependent. Similar to a mixture model, this allowed for a few distributions to generate the entire data set, but it added an extra transition rule not present in the Gaussian mixture model or in the general mixture model framework, where the distribution chosen at one time point was dependent on what distribution was chosen at the previous time point. So both of these models, the Markov model and the hidden Markov model, used discrete state space. In this case, what this meant was that even though the data itself could be continuous, the state space, or the number of data generating distributions, was finite. So we saw this plot for the Markov chain where we had these latent 3 states, and the data that we observed were the exact discrete state locations. So we had 3 unique locations or values that we could observe. And then when we generalized this, we allowed a particular state to then be a random permutation where we had Gaussian noise, in which case we had the same 3 states, but now we observed some random variable that was generated from a distribution dependent on that state. But still, the number of states underlying, the number of distributions or states underlying the data generating process was discrete. So now the question is, what if we model the underlying state as being continuous as well? Is this something that we can mathematically do easily, and what do we gain from a modeling standpoint in making this modification? So in this case, rather than allowing the number of states to be discrete and therefore have a mapping to an index from 1 to s, we're going to now modify the continuous state Markov model so that the state s is a vector in Rd. And so the state now can take any value in Rd. So again, let's compare the discrete state Markov model. In that case, the states lived in a discrete space. We could give them a label from 1 to s if there were s states. Now with the continuous state Markov model, the states live in a continuous space. So what is an example of a continuous state Markov model? The simplest possible example is something that's like what can be called Brownian motion. So in this case, the state at time t is simply equal to the state at the previous time point plus some random noise, where the noise is generated IID from some Gaussian distribution. This continuous state random walk model is a continuous state Markov model because the latent state at time t is only dependent on the value of the latent state at time t minus 1. But it's continuous because the noise added to it is a continuous valued random variable. So this isn't the model that we're going to discuss in more detail in this lecture. What we're going to discuss today is something called a linear Gaussian Markov model, which is also called a Kalman filter. With this model, what we have is a latent state process and an observed process. So this is the unobserved process and the observed process, similar to a hidden Markov model, except now we have a continuous functional form for the state process and the data process. In this case, with the latent process, we say that the state at time t, which is a vector in Rp, is equal to the state at time t minus 1 pre-multiplied by some known matrix C, so we assume that we know the matrix C, plus some random noise that is unique to time t minus 1, and we're going to assume that that's generated IID from a Gaussian with zero mean and covariance equal to Q. So this is the latent continuous state process. Notice it's continuous because the vectors st for all t are a continuous valued random variable in Rp. Then, given this latent unobserved process, we have the observed process that corresponds to it, where the observed vector at time t, which is a vector in Rd, is equal to some known matrix D multiplied by the state, the latent underlying state at time t. So we take our unobserved state at time t, multiply it by some matrix, some known matrix D, and then add some noise to that as well, where the noise process here is also a Gaussian assumed IID, but with a different covariance. So we, in both cases, have zero mean noise, but the process noise, which is the noise corresponding to the latent state process, is a covariance Q, and the measurement noise, which corresponds to the observed process, has noise V.